last lecture. Before we start, any questions about class or homework or general complaints? Okay, so last lecture we were starting to talk about feedback and two-port analysis, and I thought a good way to drive this home would be with an example. So we'll analyze a very simple feedback configuration, which is just a shunt feedback amplifier, which hopefully is one of your friends. Okay, so quick question. Why is this a good example for analyzing feedback? Or actually, what's particularly difficult about this kind of amplifier? Let's say as opposed to an op-amp with shunt feedback. In fact, is this a feedback amplifier? I mean,
the gain and the input and output impedance are finite, so you have to consider the loading.
Sure, yeah, loading is going to be very important in this amplifier. Anything else? Any other, let's say, non-ideal property of this amplifier? Potentially, depending on how we design it, right? Well, let me give you a hint. What if I make RF small? Or alternatively, what if I go to really high frequencies? Anybody have an idea? Yes?
Is that because the assumption of unilateralism breaks with this?
Yeah, there's going to be quite a bit of feed forward, right? Because usually, in our ideal model of a feedback amplifier, if you look at it, there is no feed forward. So I have my input signal, I have my output signal, and here's my feedback signal. You can see that because of the arrows, right, that means that in this signal diagram, this input signal has no way of actually making its way directly to the output. If I want to explicitly show that that can happen, then I would have to add another summing node here, go through some gain, let's say alpha, and show that some of the input signal can actually feed into the output. Now that happens because, right, a resistor doesn't care which direction current's going through it, so it will feed current back forward, let's say, into the output. Also at high frequencies, C mu will start to feed considerable amount of current in the forward direction. And so we have to watch out for that. That's because, our ideal world that we're going to keep analyzing is this world without this feed forward. And if there is feed forward present, you can expect that it's going to mess things up for us, right? Unless we explicitly take that feed forward into account. Okay. All right. So let's take the approach that we discussed last lecture. So last lecture we made the observation that we can analyze this amplifier using a two-port approach. We can break it up into two ports. So we can consider the resistive feedback network as one two-port, and I'll draw a box around it to emphasize that. And I can consider my transistor as another two-port as follows. One thing to watch out for is a transistor is actually a three-terminal element, right? So if we want it to be a two-port, we have to share a terminal. So here I'm sharing my source terminal. Obviously, that's how you get the different amplifier configurations. But the fact that this shared terminal is actually a short from the input to the output has some consequences, and we'll see that come up when we analyze some amplifiers. Okay, so if I want to connect this in shunt, say I ground everything so I have a common reference ground here, and I just simply make a connection here and here. And now I have a new two-port that looks like this, reference to ground. Okay. And so now we know that a good way to analyze this problem is to use basically two-port parameters for the feedback network and the forward amplifier. And because here the voltage on the input and output are equal, so course, I'm feeding back a current signal. If I look at the actual, let's call this I2 bar, the actual current going into the net 2-port, we can see that it's a sum of the current, let's call this I2, and let's call this I4. Okay? And likewise on the input, if I look at this current, let's call this I1, and let's call this current I3, then I1 bar, the current actually going into the amplifier, is I1 plus I3. So I know then that whatever parameter set that I use, I'd like to actually end up summing current. So what I'd like to do is represent I1, I2 as in this form, because on the right hand side the voltages are the same for both 2 ports. So I can also write I3, I4, let's call this YA for amplifier, and YFB for feedback. And now it's the same V1, V2. I don't need to define V3 and V4 because they're actually in parallel. And now I can just sum these, and I end up getting I1, I2 bar Y amplifier plus Y feedback times V1, V2 bar, because the bar domain is the same as the non-bar domain. Okay. So again, I'm really going through this slow so everybody is on the same page. Okay, so very clear, right? Any questions? If it's not clear, let's make sure we resolve it here before we move forward. Good, good. All right. I'm boring you guys. So let's now look at our amplifier. So let's look at the Y parameters of the amplifier. And as I mentioned last lecture, I always, just to make sure I'm not making a mistake, just write down these equations and then quickly derive what each one is. So Y11 is I1 V1, V2 is equal to 0. If I draw my amplifier, say a relatively simple schematic of the amplifier, let's call this Z pi, let's call this Z out, and let's call this Z mu. Then Y11 is just the input admittance when I short the output. And if I short the output, then this control goes out. It's basically shorted, right? And so then what I see is Z pi in parallel with Z mu. So Y11 is Y pi plus Y mu. Okay? And likewise, if I do the same thing on the output, if I short the input, the generator goes to 0, and I have Z out plus Z mu. So Y out plus Y mu. Admittances add. And how about the transconductance? So Y21 is I2 over V1 when V2 is equal to 0. So I'm interested in knowing this current I2 when I apply a voltage source V1 here. Well, that current is going to be exactly this current, right, the GM current, plus possibly this current, right? So this current is V1 times Y mu, and this current is basically GM V1. So in the total current, I get GM minus Y mu for my Y21. Okay? And finally, Y12. Y12 is I1 over V2 when V1 is equal to 0. So I'm applying a voltage source here, shorting out the input, and I want to find out I1. Well, if the input's shorted out, this is gone. This doesn't really matter. The current flowing here is just Z mu, right? It's V2 times y mu, and I put a negative sign, so it's minus y mu. Okay. So these are my y parameters for my transistor. Questions? Okay. What about for my feedback network? Well, it's quite trivial. I just have RF here. So short circuit input admittance is just 1 over RF. Or let's call it GF. And y12 equals y21 is minus GF, because the current direction is just negative, right? So then the total y parameters, which is the y of the amplifier plus the y of the feedback, is as follows. Remember, y11 is the input, it's y pi, which is, in this case, let's say it's a FET, CGS, y mu is j omega C gate to drain, and then plus, so let me just write this as y amplifier plus GF, GF, minus GF, minus GF. So we can just take the y parameters of the transistor and add these 4 numbers. So I get a GF here. Here the y parameters for the transistor was minus y mu, so it's minus j omega C gate to drain, and now I also subtract a GF. Y21 of the transistor was GM minus j omega C gate to drain, and now I also subtract out GF. So we can see now that the effect of the feedback is kind of the total feedback, which is the resistance in parallel with this capacitance. And finally, the output impedance of the transistor is G0 plus j omega, let's say drain to bulk, plus y mu, C gate to drain, plus GF. Okay. So now this is the total y parameters of the amplifier plus the feedback network. Questions or comments?
Why there's a CDB at the total Y21?
So if we go back to this model, Z out includes, right, RO, and it includes C drain to bulk and whatever other parasitic capacitance. Any other questions? Okay, so now you say big deal. You've got this big matrix. What are you going to do with it, right? So one of the things you can do with it is very quickly calculate the voltage gain of the overall system. Presumably that's something you're interested in. So this is 1 over ys, this is 1 over yl. And it's actually not too bad if you don't remember the formula to derive these equations from scratch. If I look here, the current I2 is just minus YL times V2. And so if I take the equation, I2 is Y21 V1 plus Y22 V2 is equal to minus YL V2. Then I have V2, Y22 plus YL is minus Y21 V1, or the internal voltage gain let's call this AV internal, which is V2 over V1, is minus Y21 over Y22 plus YL. Okay, which at low frequency is just GMRO, as you would expect, GMRL, if you like. Okay, what about the external voltage gain? So to find the total voltage gain, I want V2 over Vs. I can write that as V2 over V1, V1 over Vs, because V1 over Vs is just a voltage divider, right? So that would be AVI times YS plus Yin. Right, so it's just Yin is the admittance looking in there. And Yin, as we saw last lecture, is y11, and then the term due to the feedback, y12, y21, yl plus y22. And if I substitute now this equation in here, I get that the total gain is minus y21 over y22 plus yl times ys. Let me multiply numerator and denominator by this term, yl plus y22, ys yl plus y22, plus y11 yl plus y22 minus y12 y21. This term cancels out, and so I end up getting this equation, which looks kind of ugly, but actually is not too bad. So this is now the total voltage gain for any two-port, right? Not just this particular two-port, but since now I have some numbers I can plug in here and calculate the voltage gain, right? So I'm done. Actually, in doing this calculation, I have to admit I kind of lost sight of what the ultimate goal was. The ultimate goal is not to calculate the voltage gain, right? Why? It's so difficult to calculate the voltage gain of a... Do I have to do all this work to calculate the voltage gain of a shunt feedback amplifier? Why did I lose sight? What's the ultimate prize? Anyone? Very good. It's the loop gain. Who cares about the gain? You can calculate the gain a million different ways, right? If you're desperate, you can write KCL, KVL, crank through the equations, and you have the gain. What you can't do with KCL and KVL directly is calculate the loop gain. Okay? So now if I look at this equation, I see that there is more information in it than I actually bargained for. Because I know that the feedback is due to y12. And last lecture we defined this voltage gain when there is no feedback present. In other words, that's AV when y12 is equal to 0. And we get y21 ys plus y11 yl plus y22. Okay. So now what I do is just divide this equation by these denominator terms. So this gives me minus y21 ys plus y11 yl plus y22, 1 minus y12 y21 ys plus y11 yl plus y22. Okay, and then you observe that this is actually what we just calculated. This is AV0. That means that if this model works, this term, right, is equal to this term, which is actually what we call the loop gain. So this is 1 minus t. And so T, which is AV0 times F, is equal to Y12, Y21, YS plus Y11, YL plus Y22. If I now substitute AV0 from here, it's Y21 minus Y21 YS, YS plus Y11, YL plus Y22, and then times F. Well, these terms go away, this term goes away, and my feedback factor is simply Y12 over YS negative. Okay. Questions? Comments? Yes, Debo.
As we were discussing in the last lecture, that usually this is voltage driven, but because it's a shunt feedback and also the input impedance is lowered, we like to see it as a current. So if we do like Thevenin to just Norton transformation, we would also end up with that current source in parallel with a series parallel resistance. So in this whole like derivation, where would we fit it?
Okay, I'm glad you asked that question, because what we'd like to do is design a good, we know this is shunt feedback, so this should be driven by current. And actually, we're going to see that come right out of the equations, right? In fact, you can start to see it now. You can see that if I drive this with a source resistance that's too low, the feedback becomes ineffective, right? You see that? We'll talk about that more explicitly in a second. All right. Let's plug in some numbers, right? Let's cash in on this calculation. Okay. So this calculation, let's first calculate AV0. AV0 is minus Y21 YS, YS plus Y11, YL plus Y22. And what is Y21? It's GM minus J omega C gate to drain minus GF. Let's say YS is just GS. Let's say we just drive it with some source resistance. GS plus Y11 is J omega CGS plus C gate to drain plus GF times the second term GL. Again, let's say the load is real, and then Y22 is J omega C drain to bulk plus C gate to drain plus GF. Okay? And so then the loop gain is AV0 times F, so it's this term times minus Y12 over YS. Y12, remember, is, go back and look here, it's just C gate to drain and GF. So here is the calculation. So here is the Y12. It's minus C J omega C gate to drain plus GF. So this is AV0 times Y12 J omega C gate to drain plus GF minus times, well, let's just say divided by GS. Okay, and if I just multiply these two things, I have an expression for loop gain as a function of frequency. Well, let's calculate the low frequency loop gain just to see what we get. Okay, so as omega goes to 0, all these j omega terms go away. So here I get minus GM times GS. Here I get GS plus GF. Here I get GL plus GF. This gives me plus. Here I just get GF, and here I get GS. GS cancels out, and so I get GM, GF, GS plus GF, GL plus GF. And since most of us kind of tend to think in terms of resistances rather than admittances, let's just divide this equation by GF squared. So then I get GMRF here, and here I would get 1 plus, put 1 GF here, 1 GF here, GS over GF, which is RF over RS. And here I would get GL over GF, which is RF over RL. Okay, so this is my loop gain. Okay, so now let's plug in some numbers just to make sure our loop gain is bigger than 1, otherwise the feedback's not doing us much good. Let's say I have a GM of 10 millisiemens. Let's say RF is 10 kiloohms. And let's say RF over RS, just for simplicity, is equal to RF over RL is equal to 1. In other words, our source and load are 10K, just to make things simple. Then our loop gain would be 10 times 10, 100, divided by 4, or 25. And clearly, RS and RL are important, right? They totally are loading the totally a function. The loop gain is a function of the source and load in this expression. Now let's go back to Daybell's question. So Daybell was saying, well, you know, you'd calculate the voltage gain, but really you should drive this with a current source. And in fact, the equation tells us that. Look at the limit as RS goes to infinity. In other words, that means a current drive. Then the loop gain, the low frequency loop gain, just becomes GM-RF, becomes independent of the source resistance. This term goes away. 1 over 1 plus RF over LL. So this is a good current amplifier, current to voltage, because the gain, the closed loop gain, is actually not too strongly dependent on RS. Actually, I should say what we really care about, the loop gain, is independent of RS. So as long as RS is large enough, the loop gain, which determines all the important characteristics such as stability and all that stuff, is independent of RS. So we feel good that we could use this as a current amplifier. On the other hand, if we try to use this as a voltage input amplifier with very low source impedance, then the loop gain goes to GM-RF, and then 1 over RF, RS approaching 0, which basically goes to 0. Right, this term becomes very large, and the ratio becomes very small, and so there's no loop gain. And this is obvious, right? If you voltage drive the input, any current feedback is not going to have any effect on the input, let's say VBE or VGS or VPi, and so the feedback becomes ineffective. So to have good performance, we definitely want to drive it with high source impedance. Questions? Okay, well, if you've read Chapter 8 of Gray and Meyer, or if you've been taught the two-port approach, it's actually a little bit different than this, right? And what I like to do is, first of all, verify our calculation here using that traditional approach, and then talk about where that derivation comes from, okay? Because a lot of you haven't seen that before, and I think it's a good point to review it. So there's this, I don't know what to call it, I'll call it the loaded feedback calculation, where we take our original amplifier, and again now driving RL and RS, driven by RS, and we say, okay, this is equivalent to an open loop amplifier loaded by RL in parallel with RF and RS in parallel with RF. Okay, and we're going to talk about where these, how you know they're in parallel, right? But let's just check to see if this calculation works out. In this approach, this is my ideal forward amplifier. I neglect any kind of feedback in this amplifier, and then I assume that my feedback is unilateral. It takes a voltage at the output and feeds back a current. And so the feedback factor is just minus 1 over RF. Okay? If I wanted to subtract a current, I care about a current in this direction. So I want to subtract a current from the input. This is the current direction I should pay attention to. So this is the feedback factor. The gain of this amplifier, which is trivial to calculate, right? What's the gain of this amplifier? Well, it's just GM. Remember, it's a current amplifier. So it's GM times V pi. Well, V pi is IS times this impedance, RS in parallel with RF, times the output voltage is just, now this current flows into the output. And so now the loop gain is just this times that, and this is of course negative, so I get positive overall. Let me write this as 1 over RS plus RF, this as 1 over RL plus 1 over RF, and this is 1 over RF, right? And if I multiply everywhere by RF squared, I get GMRF on the numerator. Denominator, I get 1 plus RF over RS, 1 plus RF over RL. Same thing. Get the same thing that I got before. And this was actually a lot easier, right? Didn't have to do too much algebra, right? That was kind of a nightmare. I had to do all these big matrices. But what about high frequencies? Well, one of the differences between these two calculations is basically all these other terms, right? If you look at my calculation, for instance, in Y21, when I wrote down Y21 somewhere, I neglected this GF term, right? This is GM minus GF. What's this term? This is the feed-forward term, right? And in fact, you can see the feed-forward term subtracts from my GM. Why does it subtract? Let's get somebody who hasn't answered a question today. Why do I have a difference here? Why is the feedback why is the feed-forward subtracting from the feedback? Oh yeah, Christian.
Because the amplifier is inverting, so any signal that feeds through will be positive, whereas its amplified version will be negative.
That's exactly right. Remember, we have an inverting amplifier, right? But the feed-forward just sends the signal and doesn't flip its sign to the output. So these are actually two competing things. So the reason I paused to look at that is actually you'll see this when you run simulations, right? If you have an amplifier and you look at step response, what's the first thing you see? You actually see the amplifier at first going in the wrong direction, right? I'll give you an analogy. Let's say you have a cruise control system. You're driving your car, and you set your speed to 50 miles an hour, and you press the button, and let's say you're going 70. So instead of slowing down, the first thing the car does is it speeds up. It speeds up to 90 miles an hour, and then it slows you down to 50. Now, if a cop stops you and gives you a ticket, are you going to be able to say, my control system is screwed up? It has effectively a 0 in the transfer function, so it's going in the wrong direction, so it wasn't my fault. Okay, so the reason that we get the exact same expression here is that we neglected that feed forward when we did that simple calculation. Let's look at a final way to do this calculation. Okay, if this doesn't make any sense, don't worry, we'll review it. Okay, we're going to talk about where these equations come from. The other approach, which is probably something everybody has learned, is the so-called return ratio analysis. Okay, who hasn't learned the return ratio analysis? All right, a few people. Okay, So in the return ratio analysis, what you do, it's actually quite a powerful technique. Probably the most useful at the end of the day. What you do is you break your loop. Okay? So before I should draw this in such a way so I can break it. Okay, I'll just draw it like that. That's fine. So here's the small signal model of my circuit. And the idea is that this is a loop gain, right? By definition, it's the gain you experience as you go around the loop. And so if I break my loop, inject the signal, and look to see what comes back at the point where I broke the loop, that's the loop gain, right? And no matter what your amplifier looks like, no matter what the feed forward is, no matter what's going on, the actual loop gain should be easy to compute, right? That should be the actual loop gain. So what's the problem for doing that? Why can't I just break the loop? Let's say I'm going to break the loop over here and basically observe this voltage when I drive this voltage with a test source. Yes?
You lose loading effects on RF.
Yeah, it's not, remember, this is not a signal flow diagram. You can't just do that. There's impedances everywhere. So you don't want to disturb the impedance levels of the circuit. Here RF is loaded by these two impedances, and that has an impact on the loop gain. If I break this point and put a voltage source, effectively looks like I've shorted RF to ground. Clearly I'm not going to get the right answer. So what's the solution? It's an easy solution. I'm sure somebody knows, right? Let's get somebody new. Tim, do you know Timothy? No? Okay. What'd you guys do in 140, your equivalent electronics course? Wanted to calculate the loop gain. Chris?
Well, we actually didn't cover feedback very much last semester. We didn't plan to explain why.
Okay. All right. Well, I'm glad we're doing it in detail in this class, just to make sure you guys are ready for feedback when you meet it in the real world, or maybe on the prelim exam. All right, Drew. Okay, let's look over a simple solution, right? Very simple solution. All right, in the front, your name is Kwang. How do you say your name? Chingwo. Use the mic.
I'm not quite sure, but I guess just to kind of load the RS and the CGS and...
Yeah, that's actually a solution where you could try to figure out what it should be loaded by and drive it with the right source and loading pins. But it's not simple, right? Okay. Debo, I think you have a solution.
Inject current.
Inject current. You're still going to have the same problem, right? Because if I inject current here, I still break the loop and I still have loading effects, right? So now instead of RF to ground, I have RF floating. So this part of the amplifier doesn't even see RF. So that's not good. Yes?
Can we measure loop gain from a different point in the loop, say that current source?
Which one?
GMVGS.
Yeah, right. This is an ideal current source. An ideal current source does not care how you load it, right? So that's the point to break the loop. Because you will not disturb anything in the circuit as long as you present the same impedance to the rest of the loop as presented by the current source. So it's ideal. I can just inject the circuit with a current source. and the current source doesn't care, right? So here's the way to break the loop. So I'm going to inject a test current, let's call it Ix, and simply observe this current, let's call it IR. Okay, so notice now, as far as the rest of the loop goes, it's still driven by the same kind of source. It's still driven by a current source, infinite impedance, and as far as this current source is concerned, it doesn't care less, right? So I just short it and observe what current flows in it, right? And that's my return signal. So the loop gain, actually people call this the return ratio, but it's just the loop gain, is IR over IX. All right, so let's calculate that. So what I need to do is I need to calculate how much current, first of all, flows in this branch, and then just multiply it by this impedance, and then multiply by GM. So that's not too bad. So what I want to calculate is IX times this current divider. So that would be this impedance, let's say G0 plus J omega CL, divided by G0 plus J omega CL, plus now 1 over, let's say, yeah, it's getting complicated. Let's do it at low frequency so it's simple. I'll let you guys do the high frequency version at home. So then it's just RO divide plus RF plus RS times RS times GM. That's my return signal. Is that right? And let's say I have a RL here. So just to be consistent with our previous calculation, RL dominates the output impedance. So then the loop gain, which is IR over IX, is GM RL RS divided by RL plus RF plus RS. Okay, doesn't look very familiar, does it? So let's divide through and try to make this equation a little bit more familiar. Let's divide numerator and denominator by, first of all, RL and RS. So this gives me 1 over RS plus 1 over RL plus RF over RL RS. And now let's multiply numerator and denominator by RF. So then I get RF here and RF here, and this becomes RF squared. So then I can write this as GM RF 1 plus RF over RS 1 plus RF over RL minus 1. Okay, and that actually looks a little bit familiar. If you compare it to what we got before, you can see that this minus 1 term was missing in that previous calculation. Okay, now this is actually correct. This is the right answer. This minus 1 term is important. And this is the kind of the beauty of the loop gain approach, in that it doesn't care about feed forward. It actually will include the effects of feed forward for you. Okay.
So on the result without -1, you think that we kind of assume that no feed forward? Kind
Yeah,
of.
effectively, yeah. Okay, now I'd like to show you guys where this ideal feedback stuff comes from, or this loaded feedback. Again, I don't have a good name for it. The reason this loaded feedback analysis is useful is there are many cases where the feed-forward effects are not important, and with this feedback approach, you can quickly calculate the loop gain, the closed loop gain, and also the noise. Very importantly, the noise. Remember, before, when we talked about the noise and feedback circuits, we came to the conclusion that if you can compute the loading at the input and just make that input loading noisy, that pretty much takes care of the noise of the whole circuit. As an approximation, but a pretty good approximation. And I encourage you guys after today's lecture to go review those notes because they should make more sense now for those of you who haven't been exposed to this. Okay, so the loaded feedback idea is I want to take my circuit and again somehow force it to look like this. Okay, and this is a signal flow diagram. If I want to draw like a, let's say I'm interested in a voltage amplifier. So that means that I want to have series shunt feedback. I want to sample the output voltage and subtract an input voltage. That means that everything in the signal diagram, I want it to be a voltage. That means that my amplifier, because it's unilateral, there's only one direction for the gain. There's some internal gain A. It has some low output impedance, let's say ZO, and some high input impedance RO. And then I hook up my feedback. My feedback is also unilateral, right? This feedback doesn't allow any signals to go forward, so then I have to emphasize the fact that, first of all, my feedback does not load my circuit. So if I take a connection in shunt, it's an open. It doesn't load my circuit at all. All it does is it kind of peaks at the output voltage and generates an input voltage, which is F times V out. And at the input, I want to now subtract this voltage from my input voltage to the amplifier. So I connect it in series. Okay. So one thing that I did forget to mention is there's three good reasons for, there's three nice things about feedback and that don't show up on the signal flow graph. On the signal flow graph, the closed loop gain becomes independent of A, becomes more or less a function of F. That's the good part. But in a real circuit, what are the two other good things about feedback? What's good about, what's in here that's not in here, in other words, a benefit of feedback?
High input impedance and a low output impedance.
That's right. I forgot to mention this to you guys, but we'll look at it. The output impedance now is actually Z in, we'll show this, times 1 plus T, the loop gain. So I took my good voltage amplifier and made it even a better voltage amplifier, right? Or maybe I took a crappy voltage amplifier, and with feedback, I actually now have a very good voltage amplifier. And likewise, the output impedance is now ZO divided by 1 plus T. Okay. Let's see how we could do this, right? So now let's go from a real amplifier and try to derive something that looks like this. And in the process, we'll see all the approximations that are necessary to make an ideal voltage feedback system. All right, so let me emphasize that I have voltage at the input. In other words, I have a series connection and current at the output. Actually, I'm sorry, voltage at the output. So I have a shunt connection. Okay. So if I have two boxes, two black boxes, they're 2 ports. Hook them up in series and hook them up in shunt. the name of the game is what are the right types of two-port parameters to use. Okay, and there's only 4 of them, right? So it's got to be one of those 4. Don't guess, right? Just think about what makes sense and use that. So let's call this V1. Let's call this V2. Let's call this V3. And this V4, which is actually equal to V2. Let's call this I1. Let's call this I3. No, that's actually I1. And this is also I1. So the input currents, I1 is equal to I3. Let's call this I bar. That's the total current going into this effective 2-port, right? This is my effective 2-port. At the output, V2 of the effective 2-port is equal to V2, which is equal to V4. At the input, V1 bar, which is this voltage here, the effective voltage of this 2-port, is V1 plus V3. At the output port, I2 bar is equal to I2 plus I4. Okay. So when I set up my matrices, right, I'm going to write some relationship between voltages and currents. And what I'd like to do is set it up so on the left-hand side I have voltages that sum, and on the right-hand side I have voltages that are the same. Voltages or currents, or signals. Okay, so on the left-hand side, signals that sum, right-hand side, signals that are the same. Okay, so I kind of gave it away already. Let's call this A. Right? So what are the voltages that sum? Well, voltage V1 sums, right? So I'll call this V1. Current I2 also sums. Okay? And then on the right-hand side, what are the signals that stay the same? Well, I1 stays the same, and V2 stays the same. So so these are my dependent variables, right? Independent variables, and these are my dependent variables. So I choose input current and output voltage. Okay? And somebody gave this a name. They called it the hybrid parameters. And they're kind of weird. That's why they're called hybrid, right? You know, before we had V is equal to IZ, or Z times I. Okay, that's nice. That's all impedance. Or I is equal to Y times V. Yeah, I like that too. That's all admittance. And actually, Z and Y are just inverses of each other for most circuits. Now we've got this weird interchange of voltages and currents. Actually, it's not that weird at all. Why is this not that weird? You guys all know the H matrix really well. Yeah, right. Hybrid pi model. You use a hybrid pi model every day. Hybrid pi model gives you an output current, right, and an input impedance. And we'll see that this is exactly the same thing. All right. So, again, I always like to write this out explicitly. So I have H11 I1 plus H12 V2. I2 is H21 I1 plus H22 V2. So then, whenever let's say you're on a take-home final exam, and so you have leisure, but you also want to get the right answer, and let's say it's closed note. So you've forgotten what the hybrid parameters are, right? Just write it down, and it's very obvious, right? It's just V1 over I1 when V2 is equal to 0. Well, that's a ratio of voltage to current. That means it's the short circuit input impedance. And likewise, H21 is I2 over I1 when V2 is equal to 0. Well, that's simply the short circuit current gain. Okay? And then we're going to set I1 equal to 0, right? That gives us open circuits. So that means that H12, V1 over V2, I1 equals 0. This is the reverse voltage gain. I should say reverse open circuit voltage gain. Okay. And finally, H22 is I2 over V2, I1 equal to 0. Well, that's just 1 over resistance. It's an admittance. So this is the open circuit output admittance. Okay. And so whenever I don't like working with numbers, right? Just 4 parameters. They don't make sense to me. I like to see pictures, right? Maybe you're a numbers person, maybe you're a pictures person. I'm a pictures person, so when I see these 4 parameters, the first thing I'm hungry for is an equivalent circuit, right? And so it's very simple. Equivalent circuit should look something like this. On the input side, I should see some input admittance, which is H11. And there's also a fedback voltage H12 times V2. Then there's a current gain. So this is I1. Look, notice the input side is like a voltage source. The output side is like a current source. So here I have a current gain, which is H21 times I1. So right now I'm just drawing this intuitively, and then I'll verify. And this is also an admittance H22. Okay, let's verify that this actually is the same thing as these 2 equations. Okay? If I short V2, if I short this terminal, then V1 over I1 is just H11. Yeah, as V2 is shorted, this term goes away, and the input is just determined by H11, which is the input impedance. Okay. First equation is satisfied, or let's say the first term here. Let's look at this term. If I short the output, then this equation tells me that the current gain is just H21 times I1. Well, if I short the output, all the current of this current source flows to the output, and that's equal to H21 times I1. Yeah, that makes sense. And again, I won't bore you guys, but you can check that the other 2 also satisfy these equations. Okay, any questions? Now, something interesting that you might be surprised by. Remember, we're trying to analyze a voltage amplifier, meaning we care about voltage at the input and we care about voltage at the output. So you may have guessed that our equivalent circuit should have been voltage at the input, voltage at the output. But no, because we're making a shunt connection at the output, we're subtracting current at the output. So the output we care about is current. It's much easier to deal with currents. If you deal with voltages, you're going to confuse yourself. All right. Questions or comments? Okay, well, let's calculate the H parameters of a transistor. Okay. In fact, it shouldn't be very hard, right? Because we kind of called our most beloved model the hybrid pi model. So, well, again, I'm not going to bore you guys, so let's do the simple case. Let's assume H12 is equal to 0. So this means it's a unilateral amplifier. And again, you can go home and do the more complicated case. I know you guys have nothing better to do at home, so okay. So if H12 is equal to 0, then this is just the input impedance, right? So H11 is actually Z pi. Beautiful. Okay, in fact, I'm going to just draw. Let's call this Z out. Let's call this GM V pi. So clearly H11 is Z pi. Okay, how about H22? H22 is just the impedance looking in here. So this is equal to 1 over H22. right? And then what about GM? Well, if this is I1, V pi is I1 times Z pi, right? And so then GM times V pi, that should equal to, so that's GM Z pi times I1, that should equal to H21 I1. So H21 is GM Z pi, we usually like to call that the current gain beta. So there you have it. So for a simple unilateral transistor, in order to derive the H parameters, you don't have to do anything, right? So writing GMV pi, just write beta times IN. Anybody want to point out a difference between this transistor model and this hybrid pi model here? This hybrid pi model and this general hybrid equivalent circuit. Yes, Christian.
I think you mentioned this earlier about how the two ports are connected together.
Yeah, very good. So here I have a short across here, right? So these terminals in this general model are not connected. And that means that these are kind of like, these are floating references. So I don't have to worry about, if I load the input, it's not going to load the output in any way, right? Here, if I put an impedance down here, it just loads the input. Output is not affected. Here, if I put an impedance, it actually will affect the output, right? And that's actually a big difference that usually explains why your results are not right. And blame that. Okay, well look, we'll see a particular example of that. Okay, so now we have our hybrid parameters, and we want to analyze this feedback system. This is our feedback system. Okay. And let's say I've calculated the H parameters of my amplifier. Apparently that's very easy to do. And let's say I've calculated the H parameters of this feedback network. So I'll call this HA and this is HFB. So I have V1 I2 is equal to H parameters of the amplifier times I1 V2, and I have, let's call this V3. I have V3 I4. Remember, I is adding at the output. So these are the parameters that add. On the right hand side we have the parameters that remain the same. So on the right hand side I have I3, which is actually equal to I1, and I have V4, which is actually equal to V2. And now if I sum these two, I get V1 plus V3, I2 plus I4. Because these terms are the same, the matrices add. I1, I2, V2. And note that now these are actually the barred variables, right? These are the effective V1 bar, V2 bar, I1 bar, I2 bar. So I have, let's say V bar, let's say V1 bar, I2 bar is equal to H, I1 bar, V2 bar. Okay. So apparently H parameters are the way to go, because I can analyze my total system by just adding the respective H parameters. Okay. So this is in direct analogy with Y parameters that we looked at earlier. The reason I went through this exercise is that it's a little bit different from the Y parameters. It gives you a little bit of flavor. And I leave it to you to look at the Z parameters, right? That's for series feedback on both sides. And the G parameters, which are the inverse hybrid parameters. So exactly the opposite type, which would be for a current amplifier. Right? Current input, current output. Alright, so now how do I go from this complicated two-port to that ideal two-port feedback system where there is no loading? Right? That's the ultimate goal. So let's take my source and load into account, right? So I care about my ZS here. So this goes into my two-port. And let's connect a YL. Again, I already know, I'm anticipating that there's impedances on the input, admittances on the output. And then inside here I have my two ports. Okay. So let's write a loop equation around here. Around here I get that Vs is Zs times I1 plus H11 of the amplifier plus H11 of the feedback times I1 bar, right? That's the current going in. And I'm just summing, right? I'm not doing anything special here. So the overall H parameters are this, we know, are just the sum of the same H parameters, the amplifier and the feedback network. So here I just have H12, which is the sum H12s. The output, I don't have a source, so I just have H21 of the amplifier plus H21 of the feedback network times I1. And then for H22, you can see that YL just directly adds to the H22 of the amplifier. So I have YL plus H22 amplifier plus H22 feedback, V2. Okay. Didn't do anything special. But what I'm going to do now is very simple. I'm going to say, wait a minute, I can now pretend like instead of summing the actual matrices, I had summed two different matrices. And the two matrices look like this. 0, 0, 0, H12 amplifier plus H12 feedback. Over here, I'll take the full term. I'll take ZS plus H11A plus H11F. Here I put 0 because I'm taking all of this term and lumping it in here. Remember, that's the feedback term. So I'm putting the feedback term here. H21 amplifier plus H21 of the feedback network. And then finally, YL H22 amplifier plus H22 feedback. Okay, why did I do that? Why partition it in this way as opposed to the real physical way? Right? It's clear, right? Let's get someone new. It's an easy question for you. Remember, you get 5%. I'm serious. If at the end of the course I think back, did this person answer any questions on their own? No. 5%. So this is your chance. Yes. Vincent.
So it's because that so you have two blocks. One is the feedforward amplifier, and the other is the feedback network. Why into that two blocks?
Yeah, it's basically very simple. This is an ideal amplifier now. It's an ideal unilateral amplifier. Well, it's maybe not ideal. It has input and output impedance, but it's unilateral. And this is ideal feedback. It's ideal because you notice it doesn't load the input and output at all. It has no forward transmission, right? It just has feedback. So this is my feedback term. This is my forward term, which is 0. And these are the loading terms. So this is the output loading. And this is the input load. And by partitioning it this way, I've actually reproduced this diagram. Right? No loading on the output, no loading on the input, no feed forward, just feedback. Okay, great. So I've done it. I actually can actually draw a circuit diagram for this. And let me just assume that okay, let me just draw it first and then talk. So remember, the equivalent circuit diagram for this guy, since there's no feedback, this term just comes out. This is going to be the effective H21. This is the effective output impedance. So this is H22A plus H22F plus YL. So I've even lumped the loading of the load into my amplifier. This is H21A plus H21F times I1. And this is now ZS plus H11A plus H11F. Okay, so that's the equivalent circuit of my amplifier. Then the equivalent circuit of my feedback is H12A plus H12F times V2. And then the output is simply just copied over here without any kind of loading. Whoops. Not a very pretty picture, but the results are pretty, right? So apparently, in order to do a calculation with a real amplifier, all I have to do is calculate the H parameters of my feedback structure, lump them into my amplifier, and I'm done. It's an ideal feedback system. So I calculate the forward gain of this structure, I calculate A0 of this structure, and then calculate the feedback factor and lump all the loading of the feedback into my amplifier, and I actually can now analyze a problem. Let's do an example to drive this home. Alright, so I cooked up this example and then I spiced it, and I ran into a surprise, and then I thought about it and it made sense, but let's give you a chance to also look at this one. Okay, let's call this RL2, let's call this RL1, and let's call this R1, R2. Okay, so what kind of feedback is this? Obviously, this is the feedback network. Frank, what kind of feedback is this? Can you use the mic? That way you can hear your voice if you ever watch the tape.
It's sensing a current and voltage.
Have a 25% chance of getting the answer right. So, is it sensing a current or a voltage?
Voltage.
Yeah, V is a voltage. Someone's doing this. Yeah. Okay. And how about the input? What is it? Is it subtracting a current or a voltage? I'm sorry? Current? Okay. It's tricky. I admit it's tricky. It takes a while to get used to it. So don't feel bad if it's not obvious. First of all, that's the nice thing about the loop gain approach. You don't really need to know what's going on. You just calculate the loop gain, and that is actually the loop gain. But remember it's here I'm taking a shunt connection, right? So think about it this way. It's summing currents with the output. That means it's actually sampling a voltage. So a shunt connection here is sampling a voltage, right? And then this is a series connection. So I'm subtracting out a voltage on the input. So series on the input, right? If you forget, just draw this picture. Series on the input is voltage subtraction. Shunt on the output is a voltage connection. So this is actually a voltage-voltage connection. Or series shunt. Now there's a good reason for, instead of calling it, well, you might wonder, why don't I just call it voltage-voltage? Why do I call it series shunt? There's actually a good reason. There's a nice little trick. If you write series shunt, it'll save you a lot of work, and we'll come back to that. Alright, so this is exactly the case we analyze. We use H parameters, right? That's why it's the example that follows this long discussion. That should have been a big hint. So let's try to calculate the... So all we need to do is calculate the H parameters of this guy, right? And then just appropriately load the input and the output, and we're done. Okay? So what are the H parameters of this guy? Okay, so now you might be in trouble. Let's say you're on the test and you're like, oh god, H parameters. How do I calculate H11? Is it short on the output or is it open? God, I just can't remember, right? So what's the easy way to remember? Yeah, Debo?
Series is open, shunt is short.
Yeah, just do a transformation. The transformation is series means open, shunt means short. Right? So because I have a shunt at the output, I short it here and calculate H11. So H11 of the feedback network is R1 in parallel with R2. Okay? And then H22 of the feedback network, same trick. Series at the input means open, so looking back here, it's just R1 plus R2. Yeah, thank you. Yeah, thank you. But that means that now if I draw the equivalent circuit of my amplifier, RL1, RL2, all I have to do is just add the loading effects here. So this is going to be R1 plus R2, and this is going to be R1 in parallel with R2. Okay, that's really nice. What's the loop gain? Of course, we need to calculate H12. So H12 of the feedback network. Let's neglect H12 of this amplifier, right? It's a two-stage cascade. There's very little feedback in 2 stages. Okay, especially at low frequencies. And then what's the feedback factor of the feedback network? Well, I drive the output with a voltage. I leave the input open and just look at the voltage that appears at the input. Well, that's just a simple voltage divider. It's R2 over R1 plus R2. Okay. And because we assume that the reverse feedback of the amplifier is almost 0, then the overall F is just determined by the feedback network, right? I should add H12 amp, but this is mostly 0. Okay, so unfortunately we're out of time, but what I'd like you guys to do is analyze this problem and then spice it and then observe that you get the wrong answer. And then figure out why you get the wrong answer. Okay, see you next time.